Yes, hi guys, welcome back. I'm Aman God MV, Department of CSE. Today I'm going to discuss about the subject of analysis and design of algorithms. So let's move on to the topic. Introduction to Quicksort. Quicksort is a popular and efficient sorting algorithm used to arrange elements in specific order. It works by selecting a pivot element from a list and partitioning the list into two sublists, one with elements less than pivot and other elements with greater than the pivot. The time complexity of quicksort. The time complexity of quicksort is a critical factor in understanding its performance. In the best case scenario, when the pivot table is chosen optimally, quicksort has a time complexity of O into n log n, making it an making efficiency algorithm. However, in the worst case scenario, where the pivot element is consistently chosen poorly, the time complexity of degrade 2, which is less desirable. This highlights the importance of the pivot selection strategy in Quicksort's overall performance. Best case scenario. Quicksort is known for its efficient performance, particularly in its best case scenario, which has time complexity of O into n log n. This means that the size of the input arrays increases as the time required to sort the arrays grow logarithmically, making a quicksort a highly scalable algorithm. This best case scenario occurs when the pivot element selected during the partitioning process consistently divides the array into two or near equal halves, allowing the recursive calls to be made on smaller and smaller subarrays. The O to n log n time complexity of the best case scenario is achieved due to efficient nature of the partitioning process and the recursive nature of algorithm. By repeatedly dividing the array into smaller subarrays by performing the sorting process of these subarrays, Quicksort is able to achieve a highly efficient sorting performance even for large input sizes. Worst case scenario. In the worst case scenario, the quicksort algorithm can have a time complexity. This occurs when the pivot element selected each step is always the smallest or largest element in the unsorted partition. This results in the algorithm repeatedly partitioning the array into two very unbalanced subarrays, leading to a high number of comparisons and swaps. This scenario is most likely to happen when the input array is already sorted off or reversed sorted, reducing the effectiveness of the quick sort algorithm. To mitigate this issue, it's important to choose the pivot element carefully, such as selecting the median value or a random element from the partition. Additionally, techniques like randomized pivot selection or the use of median tree can help to improve the algorithm's performance even in the worst case scenario. Partitioning the array. First one is choose the pivot element. The first step in the quicksort algorithm is to choose the pivot element from the array. The pivot element will be used to partition the array into two or more arrays, into two subarrays, one with the elements less than the pivot and one with the elements greater than the pivot. Rearrange the array. Second is rearrange the array. Once the pivot element is chosen, the algorithm will rearrange the element in such that all the elements less than the pivot are on the left side and the elements greater than or equal to pivot are on the right side. Third one is recursive calls. After partitioning the array, the quicksort algorithm makes recursive calls on the subarrays. This process continues until the entire array is sorted in ascending order. Choosing the pivot element. First one is random selection. Selecting the pivot randomly can lead to the unbalanced partition. Second one is first last element. Using the first or last element as a pivot is simple but can result in skewed partitions. Third one is median of 3. Taking the median of first, middle and last elements improves pivot selection. The choice of pivot elements is critical to the performance of the quicksort algorithm. A good pivot selection strategy is lead to the balanced partition, improving the overall time complexity. While the simplest approach is to use the first or last element, this can result in the skewed partitions in some cases. A more reverse strategy is to select median of the first, middle, and the last elements pivot, which helps to the pathological cases. Recursive calls on partition. First one is divide. Partition the array around the pivot table. Second one is conquer. Recursively sort the left and right position. Third one is combine. Merge the sorted partitions back together. The power of quicksort lies in the recursive nature. Once the array is partitioned around a pivot element, the algorithm makes two recursive calls. One to sort left partition and one to sort right partition. The divide and conquer This divide and conquer approach allows the quicksort to efficiently track a larger arrays by breaking them into smaller and more manageable subproblems. Advantages of Quicksort: efficiency in place ordering, simplicity, parallelization. Quicksort has a time of complexity of 4 into n log n on average, making it one of the most efficient sorting algorithms available. This makes it a popular choice of sorting large databases where performance is crucial. Second one is in-place sorting. Quicksort is an in-place algorithm, meaning it can store the data without requiring additional memory space. This makes it a more memory efficient and important consideration for storing data sets. Third one is simplicity. The quicksort algorithm is relatively straightforward to implement with a simple recursive structure. This makes it easy to understand and implement, a valuable trait of developers working on sorting based application. Last one is parallelization. Quicksort can be easily parallelized, allowing for efficient sorting on multi-core system. This makes a powerful tool for handling large-scale data processing tasks. Limitations of Quicksort: first one is sensitivity of pivot selection. Second one is potential for stack and overflow. Third one is inefficient for smaller. Quicksort's performance heavily depends on the choice of the pivot elements. If the pivot element is not handled carefully, it can lead to an unbalanced partition, resulting in an worst-case scenario without the time of complexity. In the case of highly unbalanced partition, the recursive calls in Quicksort can lead to a very deep call stack, potentially causing a stack overflow error, especially in systems with limited memory. For smaller arrays, the overhead of the partitioning process and the recursive calls can overweight the benefits of Quicksort, making it less efficient compared to the simple instruction sort. Now you can, in this slide, you can all see the algorithm of Quicksort. We have reached the last part of this session. Conclusion and summary. In conclusion, the Quicksort algorithm is highly efficient sorting technique with the best case time complexity, making it an excellent choice for many practical applications. While it can have a worst case scenario, can be mitigated by carefully selecting a pivot element. Overall, Quicksort's advantages such as its speed, simplicity, and in place of operation make it widely used in a valuable tool in the realm of data storing and manipulation. Just finally, thank you for watching my video. Please like this video and please share it to your friends and families. Okay, tada, bye bye.